So let's quickly look at what we were doing last class. We started looking at mixers used in receiver and transmitter systems. So obviously the requirement of a mixer is to perform frequency translation, is to either down convert the mixer in a receiver or up convert the signal in a transmitter. What we also said is the easiest method we know of is through multiplication. You take two sinusoids and you multiply the two sinusoids and you get both the sum difference and the sum frequencies at the output, right? And this is the easiest possible way to mix two narrowband signals. As far as the metrics of the mixer go, what are we interested in? We are interested in some amount of gain, because that will make sure that the conversion gain of the mixer will make sure that the noise of the succeeding blocks will be less of a problem for us. And depending on what type of mixer it is, you may be interested in the power conversion gain or the voltage conversion gain. And this is of course defined as the output power or amplitude over the input power or amplitude. As far as noise figure goes, we will define it slightly differently. We will say it is the SNR at the input RF port over SNR at the output IF port. We define it this way slightly differently from what we did for the LNA or for a linear block, because the output frequency is different from the input frequency. And we also said that when you characterize the noise of a mixer, this is slightly different from what you would do for an LNA, because inherent to the frequency translation, you have not only noise from the input appearing with the RF getting translated to the IF frequency, you also have noise from the image band going down to the IF frequency. So therefore, even if you take an ideal noiseless mixer, its noise figure is 3 dB. The other way to do this is to apply the signal at both the RF frequency and the image frequency and then characterize the mixer, in which case you would get an ideal 0 dB noise figure with an ideal mixer. But this is obviously the more accepted way of measuring the noise figure. In terms of linearity, we discussed the IIP3, IIP2 and 1 dB compression points. Depending on what type of mixer, what type of system this is being used in, some of these linearity metrics will be important. Also specifically, we said that the cubic nonlinearity can be a problem even if you have only one signal at the RF port, because the second signal for intermodulation is already available with the LO port, and therefore the 2 omega RF minus omega LO component could fall on top of your desired signal. The other important parameter that we will be interested in is the isolation between the different ports, because the RF signal, even though it has been amplified by the LNA, may still not be very large. Imagine you are trying to receive a signal of the order of a microvolt or two. You gain it up through the LNA. Let us say the LNA gain was 20 dB. What is the amplitude of the output of the LNA? Let's say I have a 1 microvolt signal at the input of the LNA. What is the amplitude of the output? What is it? 10 microvolt. Okay. I have a 10 microvolt signal at the output of the LNA when the voltage gain is 20 dB. What do you think will be the order of the amplitude of the LO signal? In most modern IC systems, the LO signal will be of the order of a few hundred microvolts, sometimes even a 0 to VDD kind of swing is also possible. So therefore it is several orders of magnitude larger. Okay. So if you have only finite isolation between, let us say, the LO port and the RF port, the LO could completely drown out your RF signal if you are not careful. In fact, you could actually desensitize. If your isolation is very low, You might even desensitize your mixer. And so we said, if you have feed through between different ports, they lead to different kinds of issues, right? For example, if you have, let us say, a direct conversion mixer, you have feed through from the LO port to the RF port. That will mix back with your LO to give a very large DC offset. Obviously, if this isolation is time varying, that could lead to other issues also. Finally, the last parameter we talked about last class was the presence of spurious tones at the output of the mixer. Obviously, the mixer, if you had an ideal multiplicative mixer, it will only give you the sum and difference frequency components. A practical mixer may actually give you many more components because of linearity problems. It may not be a pure multiplicative mixer. Maybe in the RF path you have a nonlinearity which gives you not only pure RF, but it also gives you RF, the second harmonic, third harmonic of RF and so on. And same thing on the LO side. Now you are looking at a whole host of multiplicative components at the output. We started off looking at two-port mixers last class. So you have an input port and the output port. At the input port, you give a combination of the LO and the RF signal. Rely on the inherent nonlinearity of the two-port system to actually give you the mixing component. You are going to selectively use only the mixing component. You will have to look at the other components and make sure they are far away from your desired frequency of interest. And the simplest one we said was a square law mixer using a MOSFET using a long channel MOSFET in the saturation region. So we just modeled it as C1 Vn plus C2 Vn squared. Vout equal to C1 Vn plus C2 Vn squared being the model of the nonlinearity. And the cross term actually gives you this multiplicative quantity that you are interested in. Is that okay? Obviously, there are several different ways of implementing it, and most of these suffer from poor isolation because you are trying to combine the LO and the RF together before you feed into the mixer, and this means inherently there is very poor isolation between LO and RF ports. So we need to look at a different way of implementing the mixer. So in today's class, we are going to start looking at three-port mixers. So in other words, you are going to isolate the input RF port from the LO port and the output port. So you have three separate ports. I'll call this the IF port. So you are going to rely on a couple of things. Ideally, you want to generate only the intermodulation component, right? Only the multiplicative component. The other thing you know, what do you know about MOSFETs? What are they very good at? High input impedance. What else? What is the good property of MOSFETs compared to, let's say, other devices you know of? They make very good switches, right? MOSFETs inherently make very good switches. They have high input impedance at the gate, which can be used as a control port, and between the drain source, you can design it for very low resistance. Okay? So if you are able to use the MOSFET as a switch, you might be able to create a good mixer. That is the expectation. So the first mixer we'll look at is the single balance mixer, and to start off with, we are going to look only at active mixers. What do you understand by an active mixer? You need some bias current. Primarily, a MOSFET can be operated in two regions. One is you bias it in a region where it has a fixed bias current, and based on its characteristics, you get a particular transconductance, maybe an output impedance, and so on. Normally, that's where we bias our amplifiers, right? So those are called active circuits. If you want to use it as a passive system, you can also do that. If you bias it in the triode region, you can bias it in if you bias it in the triode region, what happens is the MOSFET behaves purely as a resistive switch, right? It does not give you any gain, and if you are going to bias it such that when the gate signal is high, it's on, it has very low resistance. So when gate resistance is off, it is completely off. As simple as that. So let us say you have a switch, okay, which goes between 2 points, which connects a third node between two different nodes. This is very easy to implement. This is very easy to implement using a differential pair, right? I'll call this 1, 2 and 3. C1 and C2 are the control nodes, and depending on the values of C1 and C2, in fact I will even make a slight modification. I'll call this C1 and C1 bar to make things even easier, right? At any time the switch is in one position, either connects 1 to 3 or 2 to 3, right? And that is very easy to implement using a differential pair, using C1 and C1 bar to control the two gates. Now suppose this is 1, 2 and 3. Suppose I have a current here. I have an input current. Let us assume I have an input current I in, and I am interested in the output differential current I out. Let us say, because it is a complementary switch, I have either C1 and C1 bar controlling the gate. The current can go either through 1 or through node 2, right? I am going to call the signal that is switching this as S of t to represent the way the current moves between the two paths. How can I represent I out? Exactly. So it's just S of t into In, right? S of t just decides whether current is going into one side or the other side. If I want to represent S of t, it is the signum function of the at the LO frequency. So it's signum of sin omega LO t So if the sin omega LOT look like this, the signum function looks like this. Of course, I have shown it at the same amplitude. It need not be the same amplitude even. It is just plus 1 and minus 1. Right? It just goes between plus and minus 1. Now if I want to find out the output current, it's very straightforward. I just need to multiply the input current with the signum function and find out what the value is. So I'm going to call S1 of t is 0.5 plus S of t. Okay, this is just a shifted version of the signum function. So S1 of t looks like this. between plus 1 and 0. I out plus. Now I need to find out, let's say, the plus and minus versions of this signal. I have still not defined what my IN is. Before I do that, I'll have to do this. So let us say IN. What will IN consist of? This is my input current. Obviously, it needs to have the RF signal, right? Anything else? It needs to have a DC component. We are talking about active mixers. It most probably will have a DC component, and this differential switch we are talking about also needs to be biased properly. So I'm going to call this IRF plus some IDC. So IRF IDC plus IRF cos omega RFT. So what I'll do is I'll call this the signal component. IRF cos omega RFT times the signum of LOT. Okay? In fact, this is iot plus we are talking about. Right? Iot plus will be IDC plus IN times S1 of t, because half the period it is 1, other half it is 0. And iot minus will be the exact same thing, but the complementary signal. The differential current I out will just be this guy. Just going to copy it and paste. As expected, this will just be this times signum of sin omega LOT. Now how do we figure out what this is? What component you get? Very simple, you just need to figure out the Fourier series components of this signum function. Right? You need to find out the Fourier series of this signum function. That is also very easy to do, it's just a simple square wave. So you are going to represent S of t as some a naught by 2 plus sigma n equal to 1 to infinity an cos n omega LOT plus bn sin n omega LOT. This is the generalized Fourier series representation. We just need to find out what these components are. What is a naught by 2 in this case? For S of t, it is 0. It has a 0 DC, it's a symmetric square wave. How do you find out an? Huh? Why is an 0? Correct. Because it is an odd signal. That you should clearly see from the way I drew the square wave. Pretty much I have drawn it as I have drawn the square wave and its fundamental component, which is a sine. And you will have, third, fifth, seventh harmonics. You have done this before, right? I don't have to say that. Bn. Again, you can use your fundamental definition to calculate what these values should be. Signum of t sin n omega LOT dt. What you can do is you can just take half the period, and for this half of the period is when the signum function is on. What is this? So it's 4 by n. Well, we will see. So 4 by t LO times 1 by n omega LO times, what is the integral of sine? Minus cos between 0 and t LO by 2. This is 2 by n pi one minus cos n pi. Okay, so dn is 0 for all even n, because cos n pi is 1 for even n, and it is 4 by n pi for all odd n. So now that we have found out the Fourier series coefficients, we will write it as 4 by pi times sin omega LOT. So that is the first term, plus 1/3 sin 3 omega LOT. Okay, plus 1/5 sin 5 omega LOT, and so on. Right? I am sure you must have done this before, deriving the Fourier series coefficients of a square wave. That's why I am going a little bit faster. And what are you going to do with this? You are going to take this and multiply it with in. Okay? But fundamentally you have to realize that this S of t has not only the LO fundamental, because you have decided to multiply it with a square wave, you are multiplying it with higher harmonics of LO also. I out of t is IDC plus times S of t. This is what we discussed before. So let us write out two portions. So let us say this is portion 1, this is portion 2 of the signal. Portion 1 of the signal is very simple. It gives you 4 IDC by pi sin omega LOT plus 1/3 sin gives you something like this. What are these components? These are purely the LO components feeding through to the output. Okay? So this is of course directly the LO feed through, and of course these are all feed through of LO harmonics. So this is happening fundamentally because even though you have a sine wave available, you are trying to use the MOSFET as a switch, and therefore fundamentally you are multiplying your signal with a square wave instead of a sine wave. What does the second portion of the curve, second term give you? So it is 4IRF by pi. So you get cos omega RFT sin omega LOT plus 1/3 cos omega RFT sin 3 omega LOT plus so on. Right? Are these the terms we desire? Some of these. But at least what we have done is we have actually managed to get a multiplicative component between the input signal cosine omega RFT and sin omega LOT. Now I'll just decompose the product of the sine and cos into two portions. So it's half of sine of, the first term will give you sine of omega LO minus omega RF plus sine of omega LO plus omega RF. Sorry. Okay. Plus I get 1/3 sine of 3 omega LO minus omega RF plus sine of 3 omega LO plus omega RF into T, and so on. You get a whole bunch of harmonics. Obviously, these are the two desired terms in the expression, depending on which type of mixer you want, whether you want an up converting mixer or a down converting mixer. The RF, if you have a transmitter, RF technically it's not RF, that would be the baseband signal, and you would be interested in the omega LO plus omega RF term. If you are looking at the receiver, you are interested in omega LO minus omega RF term. Now, let us say that we are interested in a receive mixer. So this would be a desired term. This is called the lower sideband. The other one is called the upper sideband in the mixer. What are these terms here? These are the mixing terms of your input signals with the higher harmonics of LO. This is also something which cannot be prevented. Okay? Now the good thing for you is that, because let us say if you are working with a receive mixer, you are mixing 3 omega LO with omega RF. So 3 omega LO minus omega RF will be at the third harmonic of the LO, and 3 omega, again 5 omega LO and so on. All of these higher harmonics of the LO will mix with the RF signals to actually give you components which are very far away. You can very easily filter them out. Similarly, if you are working with a transmitter, you are interested in the signal around omega LO plus omega baseband. The 3 omega LO and 5 omega LO components will again be very far away. So this may not be a big problem for you. Now the last thing is that we have assumed a perfect square wave. What happens if you don't have a perfect square wave? Or if you don't have perfect symmetry, let us say. That is what will lead to not having a perfect square wave. What will you have? Exactly. You can have two kinds of symmetry, can be lost in two ways. Okay, let us look at the original square wave we talked about. One possibility is change in duty cycle. Okay, the other possibility is just shifting the signal upwards or downwards. Let us take the second one. Let's say shifting the signal upwards. What does that lead to? It will give you a DC component. What does a DC component lead to? It leads to an RF feed through, right? If you have a DC component in this signal, this is no longer true, and what will happen is in your product term, you will also get a term which is 4RF by pi times the DC value, and that will lead to a DC term in the output. In other words, sorry, not a DC term, an RF feed through term in the output. What happens if this is asymmetric? The first case. You will see even harmonics of the LO. What does that lead to? You will have even harmonics present in the output. Anything else? You will have mixing components of the IRF with the even harmonics. What else? Will you have anything else? You may also have a DC component. You will also have a DC component. Okay? So you can have all of these things. Each one of these will affect you in different ways. It will affect your filtering. It will affect your it will affect the DC value of the output and so on. So what you actually have at the output in the frequency domain will look something like this. So this is LO, 3LO and so on. You have LO minus RF, LO plus RF. This is 3LO minus RF, 3LO plus RF and so on. Right? This is what the output spectrum will look like. So for this basic mixer we are looking at, so which looks like this. The single balance mixer so far we have seen. The easiest implementation of this. This is IDC plus the RF signal. So this is what we have here, right? At the input we are giving a square wave with a fundamental frequency of omega LO, right, at the gates of the switches, and we are interested in this output current, correct? We are seeing all of these components, and fundamentally what we are seeing is two issues. One issue is easy, you have a lot of harmonics at the output, but you can potentially easily filter them out because you will just put in a nice filter like this and you are good, because most of the other harmonics are at 3 omega LO or 5 omega LO and so on. Do you see any other problems with this? What about this guy? Right? You have what could be a fairly large LO component or LO feed through component at the output, and which may be fairly close to your desired signal. So your LO feed through component is definitely an issue. Anything else? So you need the input signal in the form of a current. Normally you are used to dealing with voltages. You need the input in the form of a current. For example, the LNA, let's say the LNA output gives you you have a common source LNA with an inductive load. The output is going to be a differential voltage. You need to find some way to convert it to a current. So that is problem. Why is that a problem? Again, voltage to current conversion will have its own set of issues. For example, let us say you have a pure VRF sin omega RFT or VRF cos omega RFT. You are sending it through a V2I converter. At the output you might get an IRF cos omega RFT, but plus you may also, because of the nonlinearity of the V2I converter itself, you may get 3 omega RF, 5 omega RF components. Again, those will mix with each of these to give you more and more spurious tones. V2I conversion nonlinearity could be a problem. So how do we get past this? Obviously there are some circuit ways to get past some of these issues, but before we go there, it is just a very simple modification of what we have here. But before we do that, let us say we are interested in the conversion gain of this mixer. What is the conversion gain of this mixer? From input current to output current. He says conversion gain is 1. Is that right? So he says, I see an answer 4 by pi. Can you look at what we just derived and tell me what it is? Is it 4 by pi? So you see this term here, 4 IRF by pi times the product of the two sinusoids, and when you decompose it you get an additional half term. So I'll replace this as 2 IRF by pi. So the conversion gain is neither of these. Conversion gain is 2 by pi from IRF to I out. Okay? If you have a V2I converter with a transconductance GM, let us say if you just use a simple transistor as the V2I converter, it will be some 2 by pi GM. Okay? Now obviously if you have this is it's not the conversion gain, but it's the conversion transconductance, right? Again, if you have a load resistance RL, you could say it's 2 by pi GM RL. So this is assuming that the mixer output load. Obviously, if you are working with a transmitter, the output will be an LC tank, LC resonant tank, tuned to the desired frequency, which will have a particular output impedance RO, RP, and you can use that 2 by pi GM RP. So if you have a down conversion mixer, that would look something like this. I'll call the inputs VLO plus and VLO minus. So let's say these two resistors are RL. You need some amount of filtering. So let us say I integrate a first order filter along with this. Okay, to get the output IF voltage. Now I need an input RF current here. What would I do? Let us say I could do this and input RF voltage. So this may have some GM, and through the GM it will convert the voltage to a current. Suppose you need to do a 50 ohm input match, what would you do? Degenerate it with an inductor. So one possibility is, this is possible with an LS. So you will get omega t times LS is 50 ohms. That is also possible. If you have enough headroom, if you want a very linear transconductor, you could degenerate it. If you have enough headroom, you could degenerate it with a degeneration resistance and get the effective GM to be 1 over RE. Okay, so that the overall gain may be limited, but you will get a very linear transconductor. Later on we are going to look at other methods to linearize transconductors, which may, or some of them work at high frequency, some of them may not. We will look at different techniques. But so far so good, right? Now, if you want to get rid of the LO harmonic, how are the LO harmonics created? First of all, the LO feed through terms. They are created through the IDC times sin omega LOT term. Correct? So can you think of a way that might help you avoid or get rid of this IDC times sin omega LOT term? Correct. So you need to add it with the negative of this minus IDC sin omega LOT term, right? 4 by pi IDC sin omega LOT, and then you subtract the same term from it, you get 0. How can you generate this extra term? A negative term. Correct, that's the easiest way. So you take a second mixer which also has the exact same DC current IDC, but it's driven with minus sin omega LOT. Is that okay? So this is what is called a double balanced mixer. So IDC plus IRF, and I'm going to take a second mixer which is driven with the opposite phase, and this thing is again IDC. And what do I do with IRF? I need to be careful, because in the process of subtracting I might end up subtracting my RF signal also, and I probably will. If I just blindly give IRF here, I will end up subtracting my RF term also. So what I'm going to do is I'm going to give IDC minus IRF. How do you do IDC minus IRF? This means that your RF port also has to be a differential port. And what do you do with these two? You add or subtract? Look at the phases I have given. I have given LO minus and LO plus for this mixer. I am multiplying it with this. What do I get at the output? For this one I will get 4 by pi IDC sin omega LOT. For this one I will get 4 by pi IDC minus sin omega LOT. So I have to add here. If I add this, what happens to the RF term? RF term also gets multiplied with minus sin omega LOT. So if I add it, minus RF multiplied with minus sin omega LO gives me double the RF term. Right? So I am giving double the RF input. I am giving 2 IRF at the input. I am getting double the amplitude I got with the single balanced mixer. So this is my I out. What will this look like? So I just have to take So this is IDC plus IRF, IDC minus IRF. So this is LO plus. So one mixer gets LO plus and LO minus. The other mixer gets LO minus and LO plus. What do I do with these? How do I add the two signals? Just sum the current. Because outputs are current so far, I just connect the two nodes together and I automatically add the currents. I'm going to add the two currents in this way. IO1 and IO2 and I out, IO1 minus IO2, right? I look at the current differentially. Okay, that will give me the desired value I need. So if I actually look at my I out, I will get, so let us say this current was I1, I2, I3 and I4. I1 plus I3, which is IO1, minus I2 plus I4, which is IO2, which is, I'll rewrite this slightly differently. I1 minus I2 minus I4 minus I3. Four by pi IRF okay, so you'll get upper sideband and lower sideband plus 1/3 of the 3 omega LO plus or minus omega RF plus so on. So you'll get all of these terms, but the nice thing is you have managed to eliminate the LO term, which was obviously a problem. What is the other advantage? Well, it's not an advantage. You are using twice the current, but your conversion gain has also increased to double. So I'll say excellent LO isolation, okay, or excellent LO IF isolation. So obviously this depends on this is a function of matching. Okay, when I say excellent, ideally it is 0, but the minute you have symmetry problems, this could crop up as an issue. The other nice thing is conversion gain GC is now 4 by pi GM RL. Because you now have differential paths on the RF, you can get by without it. So this kind of mixer is called a Gilbert cell mixer or a Gilbert cell double balance mixer. Any idea why it's called a Gilbert cell mixer? Gilbert? Gilbert would have patented it. That's an even better way of saying than Gilbert found it. Okay. Yeah, so Barry Gilbert, actually used this circuit as a multiplier. Okay. with bipolar based circuit. And in those days, obviously, multiplication in the analog domain was an important problem. So I was able to build a nice 4-quadrant multiplier using bipolar devices in this particular form. This is the MOS version of the Gilbert cell mixer, of the Gilbert cell. You are using the multiplier as a mixer, as simple as that. If you are interested in matching, what are the sources of mismatch? We have already discussed a couple of them. Obviously, the matching in the LO waveforms matter. So, isolation. So, depend on LO waveform and also the LO device match. LO device mismatch, RF device mismatch will lead to RF isolation, RF see-through issues. What else? Anything else? You could also have a case where the resistors are mismatched, and that could lead to a problem, because at the end of the day you are relying on the output voltage in this kind of circuit. So if you rely on the output voltage, you could also have mismatch on the resistors causing a problem. How do you generate this? Again, just even a simple transconductor may be good enough. Any kind of V2I converter will do. A MOSFET is a simple transconductor, but you can have degenerated, you can have other ways of performing the V2I conversion. All of those things may be applicable. However, if you choose a very complex one, you do have a headroom issue, because the way you are multiplying the two signals is by stacking them up between supply and ground. Okay? If you have too many devices stacked up, you may not be able to operate it at a very low voltage. Okay, so let us stop here, and we'll continue on Friday's class where we left off.